Hello, this will be a demonstration of Proposition 3 from Book 4 of Euclid's Elements, which says that if a first magnitude be the same multiple of a second that a third is of a fourth, and if further equal multiples of the first and third be taken, then ex equali, these equal multiples of the first and third will also be equal multiples of the second and fourth respectively. What this is going to look like is that we're going to have two magnitudes b and d, and then we will have some equal multiples a and c respectively taken of them, so that the multiple that a is of b is the same multiple that c is of d. And furthermore, we're going to have ef and gh be equal multiples of a and c themselves respectively, so that whatever multiple ef is of a is the same multiple that gh is of c. What we're going to prove is that EF and GH are then equal multiples of B and D respectively. So the use of the term ex equali here means something like through the equal, at least in the original Greek, di sua, as opposed to the Latin ex equali, like from the equal. It's better to understand it as through the equal. So between these two sets of equal multiples here, the common terms are a and c. So we go through the equal, we bridge over them to link ef and gh directly to b and d respectively, instead of going through the equal a and c, going through the common term a and c. So that's why ex equali is used in this enunciation. It doesn't have any relation to the definition. I believe definition 517 enumerated in the definitions before the propositions, but it's a similar idea, going through the equal, which is what we're doing here. Okay, that out of the way. We begin by dividing EF into a finite and clean multitude of magnitudes equal to A. EF being just a multiple of A, just any multiple of A, we know that we can do this. So we're going to divide EF into magnitudes equal to A, so we're going to have EK and KF equal to A. And likewise, we are going to have GL and LH equal to C. Again, we can do this because, Again, we can do this because GH is a clean multiple of C, so we can divide it into a clean multitude of magnitudes equal to C. And, just by virtue of there being equal multiples, we know that the number of magnitudes equal to A within EF is the same number of magnitudes equal to C within GH, right? And in this case, that's 2, right? We have 2 magnitudes equal to A within EF, and we also have 2 magnitudes equal to C within GH. But there's nothing special about 2 in particular. Again, it's just the simplest non-trivial case. So that's why Euclid works with it. But it can be 3, it can be 4, it can be 13, it doesn't matter. Okay. Now, A and C being equal multiples of B and D, and EK being equal to A and GL being equal to C, the first part we know by virtue of the fact that it was given, right? We were given the fact that A and C are equal multiples of B and D. And we made EK and GL such that they are equal to A and C respectively. And so we can substitute them in by a property of magnitudes and say that EK and GL are also equal multiples of B and D respectively, right? Because EK is equal to A and GL is equal to C, we can substitute A for EK and C for GL, so that we can say that EK is the same multiple of B that GL is of D. Now, we can also say by similar reasoning that KF and LH are equal multiples of B and D respectively, right? So the multiple that KF is of B is the same multiple that LH is of D. And what we have here are the conditions necessary to employ proposition 5.2, right? If a first magnitude, let me think this through. If a first magnitude be the same multiple of a second, that a third is of a fourth, and we have a fifth magnitude being some other multiple, and we have fifth magnitude being another same multiple of the second, that a sixth is of the fourth, then the first plus the fifth is going to be the same multiple of the second, that the third plus the sixth are of the fourth. Particularly here, we have EK and GL being equal multiples of B and D, And we have KF and LH being other equal multiples of B and D. And so we can employ 5-2 to say that EK plus KF, right, the first plus the fifth. And so EK plus KF, which is just EF, and GH, which is just GL plus LH, so the third plus the sixth, GL plus LH, that is GH, that EF and GH are then equal multiples of B and D respectively. And so again, that's just 5-2. And we set out to prove that EF and GH are equal multiples of B and D respectively, which means that we are done with the proposition, therefore, etc., Q, E, D. This is another proposition that's kind of clunky to understand with the Euclidean terms, so we can put it into more algebraic terms that might be easier to understand. What we've got going on here is we have two magnitudes. We're going to just call them again A and B, and we have some equal multiples of them. So that's going to look like MA and MB, let's say. And then of these equal multiples, we have further equal multiples taken. So that would look something like N times MA, and then N times MB. And what we're showing is that this right here, NMA and NMB, that these are also equal multiples of our original magnitudes A and B. An interesting note, or an interesting fact that this proposition lies upon is sort of like the commutative property of a multiplication. So what that would look like is saying that N times MA is going to be the same as NM times A, right? So NM times A as opposed to N times MA. So that would look something like this, and then this, right? So this is equal to this, which is basically just the commutativity of multiplication, that N times M plus A is that N times M times A is equal to N times M times A, right? That's just commutativity of multiplication. And well, we show that midway through this prop. So that's pretty neat. I like that. Other than that, I have nothing else to say about this proposition, so I'm going to end the video here and move on to 5-4.